Hey everybody, so I just wanted to hit you up with a little bit of a lesson here for what we've been talking about, maybe help you out with this lab a little bit. So if you were virtual, you won't have the LabQuest stuff that we used in class, so you can use the Moving Man again, or if you're really aggressive, you can set up a board on our, set it up like a ramp like this, and take a ball or a car or a toy or something and have it roll down. The tricky bit with that is you're either going to have to start at the top and be very clear about where you're starting it. How about I draw it on the board? You're going to have to draw the ramp or have your ramp and be really specific about where you start it, because you're going to want to start from the same spot every time. And you're going to have to time how long does it take it to go, let's say 6 inches. All right, 6 inches, or if you're better off in centimeters actually. If you have 7 centimeters, then you're probably talking about 15 centimeters, okay? 15 centimeters would be good. So you're gonna mark out sets of 15 centimeters. And you're gonna see how long does it take, start your stopwatch, let it roll to the first stop it. All right, and then record that time. And then start over and have it roll down, time how long does it take to get to the 30 mark, then reset. Or time how it's 45 marks, reset. And then time how long it'll take to get to the 60 mark and reset. And then you're gonna take that information, plug it into a data table of distance, or better yet, displacement versus time. You're gonna have a chart that looks like that, and then you're gonna translate that into a graph where delta x is up here and delta t is down there, okay? So if you're at home, you're gonna have to build your own graph, or you can use the Moving Man to make that graph for you. And then we're going to analyze it a little bit. Okay, so first of all, let's just get a little bit of this background information out of the way. If we drop a ball from a ladder, what's the direction of velocity? What's the direction of acceleration? So think on that. We'll come back at the end. So pause it or something. But think about what's the direction of the velocity, positive or negative, and what's the direction of the acceleration, positive or negative. All right? A car moving to the right when the brakes are applied, okay? So it's going to be moving to the right, but then you apply the brakes, okay? Is that direction of velocity positive or negative? Is the change in velocity positive or negative? Is the acceleration positive or negative? Same thing with a sled being pushed to the left, so you're thinking it's getting faster and faster as you push it, and then the ball getting tossed up in the air. What's the direction of velocity? What's the direction of acceleration? We'll come back to that in a couple of minutes. Don't worry about this lab quiz here. We're not prepared for that, okay? So just skip over that. Oops. So you're going to have some graphs at the end of this lab, and they're going to look maybe something like these three, all right? Position on top, velocity is red, and then acceleration is blue, all right? So we're going to analyze those, but if you're doing the virtual lab, doing the Moving Man is a great idea. You're going to set the Moving Man position at 9 meters. You're going to set the velocity at -8. And you're going to set the acceleration at 3.5. You're going to hit record down here, and then you're going to hit play, and you're going to watch him make these 3 graphs for you. Here he goes. Look at him go. He's going. Smash. All right, you can stop after anytime after he smashes, all right? And what we want to look at is the shapes of these graphs up to the point where he smashed. So let's see if we can zoom these in. No, we don't want to zoom that way, we want to zoom the other way. So we're just gonna have to take a look at that, all right? So we've got this shape, we've got this shape, we've got this shape, and if we zoom this one in, I wonder if we can. Here we go, we can zoom them all. It's the bottom magnifying glass. All right, this bottom one you can see, we don't really care about that, but we do notice here that there's a non-zero value for the acceleration graph, okay? So what do these 3 have in common? Well, if you're in calc, you're gonna start talking about derivatives and antiderivatives and how these are all derivatives or antiderivatives of each other. But what we wanna focus on now is the kind of algebra or the kinds of describing graphs that we're already familiar with. And so we're gonna do that this way. Let's pull up the one that's already done for us, okay? So with this particular graph right here, this top graph, you see that we did an analysis of it, and we came up with this fit, this curve fit. In our case, it says ax squared plus bx plus c. And that makes sense because that's kind of parabolic. We'd expect there to be a quadratic equation for it. It gives us a value of a. In this case, our capital A is 2.065. Not sure if you can see that from where you guys are sitting. Over here, actually, maybe we can make that a little bit better. Hang tight, guys. Yeah, you get to look at a big picture of me while we, no, can't fix it. Oh well, sorry. Okay, so we have a value of A, which is 0.2065. We've got a B, which is negative 1.232, and we've got a C, which is 2.359, okay? So that is going to relate to our third kinematic, right? Because where our y and our y equals for our quadratic, our y means our y-intercept, and in this case our y-intercept, or excuse me, our y-axis is position, which we call delta x. So you'll see it right here is delta x. We don't really care where it started right now. We don't really care about our c at this moment, all right? But essentially it's kind of like where we start. It's like similar to kind of a y-intercept idea, okay? So our x-axis here, we're not going to use the variable x for our variable in our quadratic. That just means the x-axis value. We'll find out that that x-axis is time, so we're going to want time. So we're going to put an t in here, a delta t, and a delta t in here. So it's starting to look like our kinematic, right? And then we bring in our b value. Our b value here is going to be our initial velocity, vi. And this a value is going to be similar to the acceleration, but because of the calculus that we're not really going to get into right now, this a value, this capital A value right here is going to be our, it's going to be equal to 1/2 a. So 1/2 of our acceleration. So the a value that's reported equals 1/2 of the acceleration of the system. All right. So that equality statement is going to help you out for the next step, because the next step we're going to look at our velocity graph. And our velocity graph here, we have a y equals mx plus b, right? Because we've got a straight line, at least for the parts that we care about. So if we look at our y equals mx plus b, right, equals mx plus b, and we kind of rearrange it, our y value, in this case, our y-axis is velocity. So we're going to put a v there, right, a velocity value there. And we're going to say that's equal to the slope. So what's the slope of a velocity versus time graph? You got to look back at your equations, think back to the notes. The slope of the velocity versus time graph is acceleration, so we can put an a there. And then our x value here in this case is time, right? So a delta t. It's a little hard for me to get the delta, so I'm just going to put t, plus our y-intercept. And what's our y-intercept? Well, that's the velocity value at time 0. So that would be called our initial velocity, right? So that's going to be v sub I, right? So our final velocity equals at plus vi. That is very similar to our second kinematic, right, I think? Yeah, second kinematic. So right here, we're using our second kinematic to describe, or if we have a graph like this, we can use the second kinematic to describe and predict that motion in the future, right? And so the a value, our slope of this graph, should be very close to double a up here, double the a value in our quadratic. It should be very close. It's not going to be perfect, but it should be close. And the reason it's not perfect, if everybody talks, we're going to find out whether that's systemic or random error. So we can check on that later. All right. Last thing we can look at is our acceleration graph. Our acceleration graph is more or less a straight line. All right. There's some hiccups, so don't worry about that. But if you highlight just this main part and we take the average, we'll get an average acceleration. And that average acceleration should match the acceleration value from our y equals mx plus b, from our velocity versus time graph. And it should be really similar to double the a value from our quadratic, from our third kinematic. And you could do the same thing. This b value should be very similar to your vi value over here. All right. So anyway, that's hopefully what we're getting out of this lab, being able to relate position versus time graph to velocity versus time graph to acceleration graphs. We're hopefully also being able to utilize the kinematics and recognize that the kinematics describe motion, especially consistent motion, whether it's constant acceleration, constant velocity, or constant position. And we're also building our analysis skills and thinking about errors along the way. So I hope this helps. I hope you guys got a lot out of it, or at least a little bit. And if you have questions, please send me an email or so.